Hello there. In this video, I'm going to show you a data structure called a stack. We're going to make a diagram of it. We're going to explain how it works. We're going to look at its typical interface, and we're just going to kind of work through the concept of what is a stack and what does it do and all that stuff. Where's your daddy and what does he do? So for starters, what am I talking about? Let me open up a little notepad here. And I'm going to start drawing. A stack is pretty simple when you first think about it. It just takes a little bit more work to really get all the details down. Imagine I have a data structure and maybe like at the bottom here, there's like some grass. And so we can say that the data structure is empty when we first start. Okay, so there's kind of a stack here, but it's empty, so there's nothing really on screen. Imagine then I wanted to add integers into this stack. So I'm going to say, let's add the integers 8, and then 2, and then 3, and then 4 for some reason. Okay, so how do we do this? The first thing we do is we take the 8 and we just put it on top of the stack. You can imagine this as a stack of boxes or a stack of books or a stack of whatever. When we add items, we're always going to add to the top of the stack. When the stack is empty, we're obviously just going to add like at the very bottom, at the ground floor, but that's sort of the top. When we add the 2 here, the next thing that happens is we just put the 2 on top of the 8. And the next thing that we do is we put the 3 on top of the 2, and so forth, right? So it's important to understand a few rules about stacks. Let me add that 4 real fast. In stacks, you're only allowed to add to the top or remove from the top. You're not allowed to add or remove from anywhere else. Let me put a T for top right here. So basically, you're allowed to add and remove from the top. So if I wanted to add, let's say, a 12, the 12 would have to go on top of the 4. It couldn't go anywhere else in this data structure. And if I wanted to remove data from this stack, I could only remove the 4. I could not remove the 3 or 2 or the 8 or anything. You're also not allowed to look at the middle of the stack. You're not allowed to look anywhere but the top. So if I wanted to look at the 3, the 2, or the 8, I wouldn't be allowed to do it. I can only look at the 4, and if I want to see that 3, I have to pop the 4 off first in order to just see what's under it. And technically, unless you have the data you added memorized somewhere else, you probably shouldn't know what's under the 4 until you actually remove it. Okay, so we can add and remove from the top. We can't look in the middle. We can't look at the bottom or anything like that. And let's do a little sequence of pops. Let me show you what the interface is really for this stack. So first off, I mean, you can imagine a stack is sort of like a vector or a list with less functionality or more restrictions. It's useful to add restrictions on top of more robust data structures for the purposes of, I don't know, kindling your imagination or allowing yourself to use easier implementations or whatever. If you're a musician or artist, probably at some point you've been stumped and you've had writer's block and you can't figure out what to create. So, I know sometimes musicians, when they get writer's block, they'll go to the swap meet and they'll buy like an old, dusty, dirty Casio keyboard from 1985, and then they'll write a full song just with that one piece of equipment, and it really stirs their creativity, or it sparks their creativity. And then when they're done, then they'll probably upgrade to better equipment. But anyway, so there's a bunch of different reasons to use, lesser data structures, although this is not really lesser. It's very useful in its own right. So let's see, the interface. So what can we do in a stack? I'm going to put S for stack. Actually, I'm just going to type this up as code. No need to use the pen the whole entire time. Let's see. So I'm going to put S for stack. Maybe I'll say, stack that holds integers, and I'll just put an S here. If you don't know how to code right now, at this point in your career, just bear with me. This is a declaration of a variable of type stack. And in C++, these stacks, stacks are a templated data structure, which means the integers that we are holding inside of the stack, they could be any other data type that we wanted to, including custom classes. So in C++, we would use these angle brackets to say, I want my stack to hold integers. And then I'm going to say S is the variable that I'll use for the stack. So, but this is not really a programming video. This is just about stacks. So if I wanted to tell the stack to push something like onto the top of the stack, I would use the method push. The method push usually has this prototype. Let's see, I'll do stack push, and it usually takes in a T-type element. And again, the T-type it's a templated data type, which means right now, if I just declared a stack that was of type integer, it holds integers, then the t would actually expand under the hood in C++ anyway at compile time to be an integer. So it would be like typing int e, right? So whenever I type t, just understand that that means one instance of a thing that you could put into the stack. So we've got a push here, and usually the return type is void, and it takes in one element to push. And that means if I'm going to actually call, let me put some comments here. If I'm going to actually call push on the stack, I've got to give it something to push, and the data type of the thing that I'm pushing has to match what the stack was declared to hold. So in this case, it's integers. So I'm going to put 8 to match the diagram up above. And then after that, maybe I wanted to push another number, so it's going to be a 2. And I'm just going to match what the diagram has up above. So 8, 2, 3, 4. So that's the interface for pushing, usually in C++. And other languages should be similar. The other thing you can do with stacks is you can pop. We haven't done that yet, but let me show it to you first. Pop usually comes in 2 forms, depending on what implementation you're looking at. So sometimes pop returns nothing. It simply removes an item from the top of the stack. And sometimes it returns a copy of the item that you're actually removing. So I'm going to put like stack here, and then like stack, just to show you that it's inside of the namespace. Oh, I don't know, maybe that's too C++-y. I'll get rid of that stuff. Hold on. So we'll maybe do this just to show you that we have 3 separate parts to this little code snip. So sometimes pop doesn't give you a copy of the thing it removes. Sometimes it gives you a copy of the thing it removes. In cases where pop does not give you a copy of the thing it removes, then you would probably want to call top right before you popped. And top will return a copy of the thing that is sitting at the top. So just to clarify, if I wanted to remove something and get a copy of it, and I had this line 13 form of pop from whatever implementation I was using, then, well, I would just call pop, and I would do something like this, auto element equals, the stack.pop. And what would happen is under the hood, it removes the item, and then it also returns a copy to me. Sorry for being too C++-y in this video. On the other hand, if I have the form that has void for pop, then I would have to do something like this. I'd have to say auto element equals stack.top, just to get a copy first, get a copy of that 4 before I remove it. And then when I'm finished, then I can say s.pop, just to grab a copy of it and then remove it. So for now, we're just going to use the form that gives you a copy of the data at the same time that you're removing it. Another thing to keep in mind, let's see, there are 2 other functions I wanted to mention real fast. So for now, I'm going to say that we only have the tpop type. You can also check to see if a stack is empty, and you can also check its size. Usually those are functions that have those names, but I'm going to do, let's see, Boolean empty, and then I'm going to say size type size. Again, sorry for being C++y, but basically in C++, a size type means an unsigned 64-bit integer. So just like a count or a size, something that's just going to be a whole number and never negative. So we have this little interface that this data structure has, and we have been calling push so far. So let's go ahead and do some pops. I'm going to say auto element equals s.pop. Maybe I'll do 2 of those in a row. Maybe instead of calling that element, I'll just say A and B, just so that we can have different variables to put our pops in. And then maybe after that, I'll do some more pushes. I'll say let's push like a 15, and let's push like a 25. And then I think that means it's probably time to erase that the top part of the diagram with the 8, 2, 3, 4 in favor of just whatever pushes and pops we're doing. So let me just do this real fast. Okay, so we did our pushes. We pushed 8, 2, 3, 4, and then I'm going to try to grab a couple pieces of data with these pops. And for pop, all you have to do is just, well, I should have mentioned this before, but first check to make sure that there is something to pop. For example, if I had a blank stack, let's say I had a blank stack right here, there's just like nothing on it. And this green line is non-standard, I'm just drawing it for fun. But imagine I had a blank stack with no items, and I decided to call pop on it. Well, you're not allowed to pop from an empty stack. There's nothing there to pop, which means that's a really, really naughty thing. In C++ and other languages, we would say that something exceptionally bad has happened. The user tried to pop something that wasn't there. And so then we would do something called throwing an exception at the user. Again, this is not really a code video, but if you know a little code, hopefully you understand try catch blocks and throwing exceptions when bad things happen. So we would just throw an exception at the user. If you don't know how to code at this point, then just keep in mind we would refuse to do it. We would say something bad has happened. We can't do that. And then when you're doing your pushes, sometimes depending on what you're using to implement the stack under the hood inside of your code, you might decide that you're using, let's say you're using an array under the hood which has a fixed capacity. If you run out of capacity and you can't actually hold any more data inside of the stack, then you would throw, if the user tried to push something into a full stack, we would call that a stack overflow. And then when we tried to pop from an empty stack, we would call that stack underflow. But for the purposes of this video, just assume that the stack is just a diagram and it has no capacity, so we can just add as many things as we want on it, or maybe we're using a linked list under the hood, which would have an unlimited capacity, or limited only by the machine's available RAM, I guess, or the program's available RAM. But anyway, so let's go ahead and try to do this pop. So let's do a pop here. Well, in the pop, we just look at the top only, right? So we say, well, you know what? Let's make this more interesting. Hang on a second. Let's make this more interesting. Let's do this. I'm going to do auto a equals s dot top. So I'm going to grab a value without actually removing it. Okay. So more interesting. So we push the 8 and we push the 2. So at that point in time, actually, let's trace this from scratch. So we have like an empty stack here. There's nothing there. And we're going to push the 8. So the 8 goes on the very top, just like we did last time. I'm going to put an 8 there. And then we're going to push the 2 next. So the 2 just kind of goes on top. And then the next line, line 12, we're just checking the top. Remember, we're allowed to actually look at the top if we want to. So since 2 is at the top, that means A is equal to 2. I'm going to put a 2 here to remind ourselves that A is now equal to 2. Then we're going to do a push 3. So I'm just going to stick a 3 on top of the stack. And then we're going to push a 4. 4 is on top of the stack now. Again, we're not allowed to look at anything in the middle, anything but the top. So for example, when the 3 was on top, we could look at it and remove it. But now that we have a 4 on top, we can no longer even see the 3. It's not available to us anymore. So then we're going to pop and put that value into B. So, you know, what's at the very top? It's a 4. So that means we're going to actually remove the 4 and stick that into B. So I'm going to put 4 right here to remind ourselves that B is now equal to 4. And for the purposes of this video, you can just imagine that this, you know, the top of the stack is just totally gone, deallocated. Depending on what implementation you use, you might want to think about crossing it out. Maybe there's like some junk data there now, but for the purposes of this video and this diagram, we're just saying it's gone. So it's just totally gone. Okay, then let's do another pop. So we're going to pop, and that's going to become C. So obviously the top is now the 3. So that means the 3 is going to go into the C variable. So here's a 3 right there. Then the 3 gets deallocated. And now the top is the 2. So then we'll push a 15 and we'll push a 25. So again, we just put those new items on top of the stack. Even if there was stuff there before, it's gone now. So we're just going to stick the 15 and then, whoops, my penmanship sucks. Now it's going to be a 15 and a 25 on top of the stack. So we got this. And then 25. And then we're done adding our stuff. So the other functions that we talked about are empty and size. At the very beginning, when we had just an empty stack like that, if we were to call on the empty function, it would tell us true, the stack is empty. And then every step after that, where we had some data in the stack, like as soon as we even added that 8 at the very beginning, from that point forward, then empty would have returned false to us saying, no, the stack is, it's not empty. The size would have changed during every step of the way. So, you know, at line 10, the size would have been 1 after we're finished with line 10. After line 11, the size would have been 2. 12 wouldn't have changed the size, so it still would have been 2. 13 would have upgraded the size to 3, and then 14 would have upgraded the size to 4. Once we popped, after that pop was finished, it would have been 3 again. Then the second pop would have brought it back down to 2, and then those 2 pushes would have put it back up to 3 and then 4. And so then the final size, whoops, that was horrible. The final size of the stack is 4, and you can tell that there's just 4 items. Another way to double check yourself if you're kind of trying to trace this on your own is just count the number of pushes and subtract the number of pops. So how many pushes do we have? 1, 2, 3, 4, 5, 6. So that's like 6 minus however many pops we saw. We see 2 pops. So 6 minus 2 is equal to 4. So, you know, when you're writing this sort of thing down on, you know, like as a diagram to practice, then you know it's a 4 just by looking. But what if you did something wrong? It's a great idea to double check yourself at all times. So 6 minus 2 is 4. So we know that the size of the stack is 4. Looks pretty good, and we know the values of A, B, and C, and you know, one of those was top, 2 of those were pops. And yeah, okay. So notice something though that's kind of peculiar about the data that came out. If we added the data, like I guess while we were adding the data, we added first an 8, and then a 2, and then a 3, and then a 4. I'm just looking at the pushes right now, and then a 15, and then a 25, right? So we added the data in that order. But then when we grabbed the data out, let me put this in, put maybe like a red bracket or something. When we grabbed data out of it, the pops and the tops gave us 2, and then a, okay, never mind. That was not a pop. It gave us a 4 and then a 3 if we're just talking about the pops. But look at the first 2 items. Sorry. Look at the last 2 items right before. I didn't draw this very well. Imagine that we had just pushed the 8 and the 2 and the 3 and the 4 only. Forget about these other pieces of data. So at this point, when we start calling our pops, we have only an 8, 2, 3, 4 stack, right? So the data that comes out then, notice how it comes out as a 4 and then a 3. If we're removing data from the stack. So notice how the 4 and the 3 are backwards. Notice also, like if we kept popping out data, you know, we got the 4 and then we got the 3. What's the next thing that would come out? It would be the 25, right? And then it would be the 15. And then it would be the 2, and then it would be the 8. So if you really think about it, the stack is reversing our input data. We added a 3 and then a 4, but we received a 4 and then a 3. And of course, it's a little bit muddled because we have some pushes in between, some tops and pops and stuff. But just looking at what goes into the stack, it's backwards, right? 8, 2, 15, 25. Let me finish this this push sequence up here. So we added 3 and 4, and then we added a 15, and then my penmanship, dude. 15, and then we added a 25. So if you look at the data that comes out, this is like a 15 and a 25 backwards, and then the 3 and the 4 are backwards, and then the 2 and the 8 are also backwards. And so one thing that a stack does is it reverses data. Let me give you a cleaner example with no pops in between the pushes, just to show you what we're talking about a little bit more clearly. Okay, so I'm going to do maybe like another code page here. Whoops. Do that, and then I'm going to say, got our stack, and we're just going to push in some data. And then we'll just say s.pop, and maybe I'll just do that however many times. 6, 2, 3, 4, 5, 6. So now just a very quick trace, because this is basically the same data that we had last time, just not as intermixed. So I'm going to do like the bottom of the stack here, and then, well, I mean like an empty stack. That's not really a bottom of a stack. So we're going to push an 8, and then we're going to push a 2, and then we're going to push a 3, and then we're going to push a 4, then a 15. Ugh, gotta work on my 5s, dude. Okay, and then 25. Okay, one more time. Oh yeah, I guess I gotta slow down. So what's going to come out? Remember, the top is the only place that will give us data. So if we start popping all these one by one, we're going to end up with a 25 for that first pop. Maybe I should write it down over here. Do like a 25, and maybe I'll add some line breaks in the code here so that it's easier for me to write with a pen. Do this and that. Okay, so the 25, I'm just going to do a red line through it to designate or to denote deallocation or just like goneness. Then the top is at the 15. We do another pop, it's going to be 15. Oh, I did my first perfect 5 today. And then the top of the stack is now at the 4. So then the 4 is going to pop out next. And then the 3 is going to pop out next. The top is now at the 3. So the 3 is coming out for that pop. We deallocate the 3. The top goes down 1. And then we pop. It becomes the 2. That's deallocated now. And then we grab the 8 because that's where the top is. So now we've grabbed all of our data out. And I just want you to look at this one more time. Notice the data is 8. The data that went in was 8, 2, 3, 4, 15, 25. The data that came out was backwards. 25, 15, 4, 3, 2, 8, or 8, 2, 3, 4, 15, 25, if you kind of like look up. So a stack is a data reverser. A stack is also known as something called a, let's see, last in, first out data structure, LIFO, or first in, last out, FILO data structure. What that basically means is just it's reversing the data, or priority goes to the item that is the youngest. So if you looked at the stack at the point where we were about to remove the 25, 25 was the most recently added, or the youngest item, or the item with, I guess, the timestamp the furthest in the future, however you want to look at it. And that's the item that came out. So if you think about it, it was the last item in, and therefore when we did another pop, it was the first item out. So LIFO or FILO. And, you know, this 8 down here, that was obviously the last item that we were able to grab out of it. So when we said, you know, pop, our final pop before the stack became empty, the 8 was definitely the first item in. So first in was the last out. If you really want to, you can kind of like jumble these acronyms. I think most like people just use LIFO or FILO. For me personally, in my personal life, if you say something to me that I understand, I think it's probably fine, but it's non-standard. I like to say, you know, Foley, first out, last in. That definitely makes sense. It's just not very common. Another thing that I like to do for fun is I'll mix up the FILO and I'll say lo-fi because last out is first in. And now I'm cooler than other computer people because I use the word lo-fi. I've now got like a giant mustache and like a little like swap meet shirt, and I have craft beers, and I have work boots on, and I roll up my jeans, and my sleeves are rolled up and all that stuff. You know what I'm saying? I'm cooler than everybody else now because I used lo-fi. Anyway, so we used integers. It's just important to understand that in modern coding, I think I might have mentioned this before with the T's. These stacks are templated data structures, which basically means we can hold another data type besides integers as long as we declare what the stack will hold in advance. So instead of integers, you could imagine there's like a custom class, like my class. Every single, you know, item in the stack is actually a full instance of a my class object, or you know, floats or strings, or just, you know, any data structure you want. You could put another data structure inside of a stack. People do that sometimes just for fun. You could take a vector and stick it inside of a stack, a list, put it inside of a stack, you know, whatever you want to do, just to show that you understand everything. So again, by the way, the stack is empty. If we tried to pop from it at this point, this would be called a stack underflow. We would probably want to throw an exception at the user, or just say we're not allowed to do it. Let's see. So I guess now I should tell you some common uses for stacks. I'm looking at my notes right here. Obviously, our stack has reversed the data, so stacks are kind of good for data reversing. Imagine if you had like a word and you wanted to detect if the word was a palindrome or not. You would just like put all the letters of the word into your stack and then grab them back out and see if the word was still in the same order. If it was, then your word was probably a palindrome. If you don't remember what a palindrome is, I'm going to write down the word radar in reverse from backwards from back to front, right? It's the same word, so that's a palindrome. You could also use stacks kind of as a trail of breadcrumbs. Like you could imagine that early implementations of browsers had your browsing history in a stack somewhere, so that every time you visited a web page, then some kind of block of information, maybe like a custom class instance, was put onto a stack somewhere, and it contained information about like when you visited the web page, what the URL was, and just like whatever it is that the browser wants to remember. And then later when you hit the back button, then you can imagine the browser is popping from the stack in order to go backwards in your history or your Spotify playlist or whatever it is you're doing. Honestly, these systems are much more advanced than just using, vanilla stacks now, but you could imagine doing something on your own for fun, or just what it might have been like in the very beginning. I'm going to erase Foley because that's just cringe. Lo-fi, I think, is way cooler. So trail of breadcrumbs, like, browser history. You could also imagine undo history, like if you had a, I don't know, like a text editor of some sort, or like a image editor of some sort. Every major change that you did to it, maybe the program under the hood is adding your change to the stack, and that makes it easier to sort of reverse your changes as those changes are popped. And there's like a sort of mathematical uses, like balancing parentheses and things, but I'm not going to talk about that too much. One of the most important uses for stacks inside of your computer is actually the call stack. I'm going to talk about that in a future video, but again, remember each little item on the stack, it could be a different data structure on its own. It doesn't have to be an integer. So imagine that I bundled up a bunch of information about a function call, and I called it a call frame, and every time I called a function, I just stuck a call frame on the stack. That's basically the call stack. But that's for another video. Anyway, so let's see, is there anything else that I wanted to show you? I think we're actually done just talking about the basics of stacks. I'm not talking about time complexities or anything like that in this video. Check a future video if you're interested in time complexities per certain implementations and so forth. But for now, this is how a stack works. It's a FILO or LIFO or lo-fi data structure. Nobody's going to say lo-fi but me, just FYI. But maybe everybody will start doing it now. I don't know. If it becomes a trend, okay? You heard it here first. Give everybody this link. All right, I hope you feel like an expert on stacks at this point. I hope you had a little bit of fun and learned a little bit of some stuffs. I'll see you in the next video. Hey everybody, thanks for watching this video again. From the bottom of my heart, I really appreciate it. I do hope you did learn something and have some fun. If you could do me a small little favor, could you please subscribe and follow this channel or these videos or whatever it is you do on the current social media website that you're looking at right now. It would really mean the world to me, and it'll help make more videos and grow this community, so we'll be able to do more videos, longer videos, better videos, or just I'll be able to keep making videos in general. So please do me a kindness and subscribe. Sometimes I'm sleeping in the middle of the night and I just wake up because I know somebody subscribed or followed. It just wakes me up and I get filled with joy. That's exactly what happens every single time. So you could do it as a nice favor to me, or you could troll me if you want to just wake me up in the middle of the night. Just subscribe, and then I'll just wake up. I promise that's what will happen. Also, if you look at the middle of the screen right now, you should see a QR code which you can scan in order to go to the website, which I think is also named somewhere at the bottom of this video. And it'll take you to my main website where you can just kind of like see all the videos I published and the services and tutorials and things that I offer and all that good stuff. And if you have a suggestion for clarifications or errata or just future videos that you want to see, please leave a comment. Or if you just want to say, hey, what's up? What's going on? Just send me a comment, whatever. I also wake up for those in the middle of the night. I wake up in a cold sweat and I'm like, it would really mean the world to me. I would really appreciate it. So again, thank you so much for watching this video, and enjoy the cool music as I fade into the darkness which is coming for us all.